So thank you very much for inviting me and sort of almost insisting that I should be here. And I really appreciate this because I think it is very important for me to say the influence and impact of Abdus Salam on what we have done in India. So I just wanted to, I augmented my talk actually hearing all the other people say many things about Salam. So my technical talk, I will just go a little bit faster. So, okay. All right. So first, I'd just like to very briefly mention to you the impact of Abdus Salam on string theory in India. I think he had an impact on many other subjects, but since I'm myself a string theorist, a high energy physicist, I will just restrict my comments to this subject. So in 1985, we at the Tata Institute wrote a paper actually in string theory. That was the first paper sort of coming out of our group, and I think also in India. And so promptly next year, when there was this meeting at the ICTP in Trieste, Salam invited me, and I still remember that there was this usually very wonderful parties before the meeting, and on the terrace of Adriatico. And he somehow found out who I was. I think he might be wondering whether I am a man or a woman, because my name ends with a vowel. But anyway, we met, and I think after that, almost every year for 20 years, I went to the ICTP actually doing various activities with Kaiser and Yogesh Pati and others. So that was the introduction to the ICTP, and in fact, I would like to say that at one point, our entire string theory group, all the members of the Tata Institute string theory group, were one time or the other associates of the ICTP. So, okay. Now, I think there was an enormous resistance to doing string theory. Now I can at this stage say everything very openly. In the corridors of the Tata Institute, people used to say, oh, this is not science, what are you doing, etc., etc. So we had a very great supporter from Abdus Salam, who was strongly behind us in doing this activity in India, and his encouragement and strong association with the ICTP greatly helped us to build this, what I would like to say was an outstanding group, and this activity in India took very, very good shape, and it's, I think, internationally one of the best groups in the last couple of decades in Indian science. So I'd like to really put on record the fact that Salam's encouragement and his insistence that this is an important thing to do played a very important role, because we were very young. I was half my age at that time, literally. So there was something about this persona of Salam which I'd like to mention to you. So just one little story that, as you know, that he used to sort of come in and out of lectures. And one day he came and sat beside me and nudged me a little bit that, why are you doing all this? You know, Steve said that it is very difficult thing to do. So firstly, I didn't really connect who this Steve was. So then I realized that he's talking about Stephen Weinberg. Then I said that, look, Steve Weinberg is much older than I am. So let me do this. So anyway, he had a very sort of a very jovial and a very humorous personality, which made people feel very comfortable actually. And I was very happy that almost every year when I was there, at some point I have to go to his office and summarize what is happening, especially towards the end when he was not very well. His close young friends used to go and summarize what's happening in the area, etc. And persistently the question was, what about gravities? What is happening about quantum gravity, etc. Okay, so this is what I wanted to mention about Salam very briefly. I can say many more things, but for limitations of time, I'll restrict myself to this. And now I want to come to something which certainly very subconsciously, almost I'm sure, was inspired by the ICTP. This is the photograph of the International Center for Theoretical Sciences of the TIFR. It's the Tata Institute of Fundamental Research in Bangalore. And the campus is almost complete. A few things are happening, but this is how it looks. It's quite big. It's about 20,000 square meters built up, and over a land size of about 80,000 square meters in Bangalore. I just would like to say very briefly what we do. So, what is basically the goal of the ICTS? So you realize that this is S and not P. I think this was this. So I was mentioning to Salam's son yesterday about this, and he said that father would have definitely done S today. So, because I think the ICTP activities also, in a sense, are now very inclusive of other areas of physics, science. So the main idea, the main ambition is to bring together physicists, astronomers, cosmologists, biologists, mathematicians, all from all over the world, just under one roof. I mean, this is the one-line summary. And the idea is to work together to solve the most challenging questions posed by nature, and to contribute to the creation of scientific culture in India. This is a very important thing to do. I don't want to detail why it is so important for us to work towards creation of scientific culture in India. So this is in a nutshell what the ICTS does, and this is in a nutshell what we have done in the past 7-8 years. So we have organized over 100 programs of various lengths, of various types, including the last one, which was Strings 2015 in ICTS in Bangalore. And we have already a research faculty of 15 spreading over all the basic areas of the theoretical sciences, and with about 15 students, 15 postdocs, and many visitors actually. So the population is of the order of 100 in the institute per day. And these are the three main the main points of the mission of the ICTS. Visitor-driven programs, in-house research is excellent, and these sort of talk to each other all the time. And of course, science outreach and public engagement, which is a very serious thing at the ICTS actually. Okay, so having said these few words about what it is, let me show you some of the buildings. This is the Panini Library. This is the campus inauguration in June. And this is just outside the Chandrasekhar Auditorium. And the last slide here is that in order to commemorate the memory of Abdus Salam, we have named one of the 3 academic blocks after him. There are 3 academic blocks, one named after the mathematician Harishchandra, the other after the biologist, the physical biologist G.N. Ramchandran, and the third one is after Abdus Salam. Okay. We also have Abdus Salam Memorial Lecture. The first one was delivered by Fernando, and the one that was just delivered in last December by K. Vijayaraghavan. So this is what I wanted to tell you about what has happened in Bangalore, very much inspired by Abdus Salam and ICTP. And of course, I would like to mention here that the KITP and its modeling also was very important for us, including the very strong encouragement and support from David Cross. Okay, so that is the end of the first part of my talk, and now let me get on to the technical part of my talk. So I want to talk about Chern-Simons theory and coupled to fundamental matter. So this the work is mainly contained in this paper. It took a long time to do it for reasons I will sort of mention to you briefly. So the two things that we basically would like to work with today are Chern-Simons theories coupled to bosonic matter and Chern-Simons theories coupled to fermionic matter. As you know, that Chern-Simons theories are sort of rather very well studied. Without coupling to matter, they are topological theories. They have no local degrees of freedom and have had many very ubiquitous applications in mathematics and in also in condensed matter physics. But we would like to now study the theory which has couplings to matter for reasons I will explain. Now, there are various reasons to study this theory. And as you know, Chern-Simons theories are characterized by a certain level, which is given over here. For a compact group, this level is an integer, and we will be working with compact groups, so the level k is an integer over here. And the idea would be basically to, it will be great to solve this theory for finite n and k, but we look at the 't Hooft limit of this model in which n goes to infinity, k goes to infinity, and this number, which is this 't Hooft coupling, is kept fixed. And I mean, I would like to tell you that this theory is barely soluble. This is an interacting three-dimensional field theory, and very few such theories are known to be soluble actually. So this theory barely soluble, but we have solved this, and with many other groups also had contributions. And I think one of the most important results of this entire development, which involved groups from the Weizmann Institute, our institute, from Harvard University, etc., and Princeton, various groups of people. Ultimately, the result which I would like to mention to you is that there is a Fermi-Boson duality in 2 + 1 dimensional quantum field theory. Okay, and this duality basically reflects the so-called level rank duality of Chern-Simons theories, which I will elaborate on as we go on. Okay, so this is the main result. And today's talk essentially confirms this again for the S matrix. So what is the evidence for this? Let me just summarize the evidence for this. So I will not be proving anything, but the evidence is the following: that if you take fermions coupled to Chern-Simons theory, regular fermions coupled to Chern-Simons theory, and they are massless, so they are conformal, and you take bosons coupled to Chern-Simons theory in the Wilson-Fisher limit in which the theory is critical, then, and you compute the spectra of these two theories, then the spectra of these two theories are identical. So this is something which I want to explain over here, that the spectrum is precisely given by this simple formula. This is the spin of the operator, and this is the dimension of the operator. And so you have all these higher spin modes plus this 2-0 entry over here. And for the fully interacting conformally invariant theory, this spectrum is independent of the coupling constant. This was the first hint which we got in our first work that there might be a Fermi-Boson duality in 2 + 1 dimensions. So this is the first thing. The second thing was the duality of the 3-point function that is over here. Let me explain that to you. So Maldacena and Zeboidiev computed in an ingenious way the 3-point function of higher spin currents in the fermionic theory and higher spin currents in the bosonic theory. And then they found, if you, with some additional work by Aharoni and his collaborators, that this 3-point function of these higher spin currents for the group UNF at level KF is identical to the 3 bosonic current calculation for the group UNB at the level KB, provided NB and NF and KB and KF are basically related by the level rank duality. Okay, so this is a definite result which encourages you that this result is again true. All right, the third evidence comes from the exact computation of the thermal partition function on S2 cross S1 in both these theories. So this is really a tour de force calculation, but I would like to mention over here that there is a very important work by Blau and Thomson, George Thomson, for pure Chern-Simons theories, which actually made it was a very important input in this result, which of course is much more difficult to do because it is coupling the theory to matter. Again, you find that if the parameters are related by this level rank duality, then the partition function of the fermion theory is the same as the partition function of the boson theory. And in the above, of course, over here, the bosons are at the Wilson-Fisher critical point. This result has been generalized by Meanwala and other students and collaborators to include also supersymmetric theories and also theories with mass deformations, etc. But this is the main result, the basic result. Okay. Now, let me tell you a few facts about pure Chern-Simons theory, which would be very useful later on. That the pure Chern-Simons theory, as you know, is a topological field theory on a three-manifold. And the most important property of that theory for our type of work was this formula, actually, for the expectation value of Wilson loops. So if you look at Wilson loop in the representation n at level k, of the UN group, representation r at level k, then it is identical to precisely mod k minus n for the gauge group. Level is minus k, and the representation is r twiddle, where r twiddle is obtained from r by simply interchanging the rows and columns of the Young tableau. Now, it is this formula actually that implies in the partition function the Bose-Fermi duality. So I thought I'd just mention that to you. And the last little thing which I will need at the end of my talk, or somewhere in the middle, is that Wilson loops of the Chern-Simons theory were studied by Ed Witten in his very famous paper on the Jones polynomial. And for later use, I would like to sort of note a formula. If you take an ordinary simple curve with the topology of a circle in S3, Chern-Simons theory on S3, then this formula is true, that the expectation value of W square is actually equal to the expectation value of W whole square. And this ratio turns out to be sine pi lambda upon pi lambda. And this is a number which will be important for us as we look at the S-channel S matrix. Okay, so these are some preliminaries. And I want to now study the scattering of colored objects. Okay, this is not the scattering of gauge invariant objects, but colored objects in the Chern-Simons theory. So you take two colored bosons and scatter them. You take two colored fermions and scatter them in some representation of the gauge group. And the question is, what are the results? So these are the results. So firstly, in the T and U channel, the S matrix is calculable at large n. Means you can compute at large n in axial gauge. This can be calculated. And you can verify it is unitary, and it exhibits Fermi-Boson duality. So this is a nice result. Secondly, the S-channel S matrix cannot be obtained from the U and T channels by crossing symmetry. So there is a breakdown of crossing symmetry in Chern-Simons theory, which is a thing which people, in S matrix theory, because of analyticity, that there is crossing symmetry between S, T, and U channels. But here there is a failure of crossing symmetry. So I'll explain to you why all this is happening. Because the S matrix is not analytic. And it turns out that unitarity ultimately requires a delta function in the forward scattering. So I'll explain what this Aharonov-Bohm-Ruiz-Senaz result is. And all this is because the spectra of these theories contain anyons. By anyons, I mean that if you have a charged particle described by a certain current density, then it automatically generates a certain flux. And this is the Gauss law of Chern-Simons theory, which basically says that the spectra has anyons. Okay, independent of the gauge group. All right. So let me continue with the summary of results, because the formulas are too complicated and maybe you might get lost, but there are some take-home points. So these standard, as I said, the LSZ formalism of quantum field theory fails because due to Gauss's law, the Chern-Simons gauge field never decouples from the colored matter. You see, usually in S matrix theory, you have this assumption that you can actually switch off the interaction. And because you can switch off the interaction, when the interaction is not there, the S matrix is 1. Okay? But in this problem, you cannot switch off the interaction, precisely because of that Gauss law. So the S matrix is actually not 1 plus something, but it's something plus IT. Okay, and that's the delta function that I was talking about. Okay, so that's a simple point. So hence, you need to have a modification of the definition of how to extract the S matrix. So the LSZ formalism doesn't work here. So I'll explain to you how to do this. And this modification, which I will talk about, leads to modified crossing relations for the analytic part of the S matrix. And the proposed S matrix, S-channel S matrix, passes many tests like unitarity, duality, and a correct non-relativistic limit, but as yet has not been calculated from first principles for technical reasons. I'll explain this to you now. Okay, so let me just give you the answer. So the final formula for the S matrix written as 1 plus IT, okay? The T is given by this formula, okay? This is the forward scattering delta function. I'll explain this delta function, how it comes about. And there's a very specific coefficient here. And this is a trial formula for the S matrix, in the T matrix, in the S channel, which is obtained essentially by doing a naive crossing symmetric procedure on the T channel T matrix. Okay, so these are some formulas actually, don't worry about these formulas. Okay, so this is the final answer, I claim, of the S channel S matrix. This is the most important result of this work is this one. All right, so now let us try to understand how it came about. So some preliminaries of scattering theory. Clearly, we have particles which transform as in fundamental representation of UN, antiparticles, let me call them A, under anti-fundamental representation of UN. It's like quarks and antiquarks of SU3. So there are three basic scattering processes: particle-particle going to particle-particle, particle-antiparticle going to particle-antiparticle, and anti-anti going to anti-anti, which is basically related to the first process by CPT. Okay, so these are representations. So they scattered. I mean, they combine into simple other representations of the gauge group. For example, if you scatter particle and antiparticle, then clearly you will essentially have two channels. One is the singlet, and the other is the adjoint. Okay, and so on for the other ones also. And this is just a simple diagram to illustrate the scattering process. So if you go this way, this is the T channel. If you go this way, it's the S channel. And let me just go a little bit quickly. So what you do, how to solve this type of problem is you set up the Schwinger-Dyson equation for the 4-point function, and you try to solve this integral equation actually. So this integral equation is very difficult to solve unless you put the center of mass momentum, or this Q3. You see there's a Q momentum over here which keeps on getting conserved as you go down the diagram. For example, if you look over here, there is this momentum Q. So if you add another gluon line and another one, etc., this Q will keep on going. Now, the technique of solving the integral equation, or the integral equation is soluble in the limit in which this Q plus minus, or Q1, 2, one component and two component can be set equal to 0 over here in this equation. So this integral equation is soluble in those cases in which only the third component of Q is active. Now you can set Q1 and Q2 equal to 0 only in the T and U channels, because in the S channel this object Q is actually the center of mass momentum, and you cannot set this center of mass momentum to 0 because then the energy momentum relation becomes space-like, and that doesn't make any sense. So cutting a very long story short, this integral equation can only be solved in the T and U channels in this particular limit in which Q is simply Q3, and in the S channel this cannot be done because then the center of mass would be space-like. Okay. I've said over here in so many words what I already said, and what happens is that in the T and the U channels, the fermionic and bosonic S matrices are all calculable, they are unitary, and they satisfy this duality relation. This is the level rank duality, but you have to be a little careful because now we have massive fermions and massive bosons, and the masses are related by this simple formula, which involves the 't Hooft coupling lambda. Okay? All right. So you accept my point that we can compute in the large n limit the S matrix in the T and the U channels exactly in the large n limit. In the S channel I cannot do this calculation, nor can I use a crossing symmetry to evaluate the answer in the S channel. Okay? And the reason is, as I said before, that there is a violation of unitarity in the S channel. And there are two sources of violation of unitarity. Firstly, there is a delta function in the forward scattering, and hence the S matrix is not unitary or not analytic. And second, that the standard formulas of crossing symmetry cannot be used. So it turns out that the S matrix in the T and S channels are in fact related by precisely this factor f of lambda, which was the expectation value of the Wilson loop in the pure Chern-Simons theory. And this is dictated by gauge invariance. So I'll explain these two facts, and I think this is the most important take-home summary for you. All right, so the source of the delta function. So I'd like to tell you that the Aharonov first point is that the Aharonov-Bohm famous paper actually is wrong. Is wrong because the answer is not unitary. Okay, this paper is from 1954 or something, or 59, and 20 years later, this physicist Ruysch-Senars in 83 basically found out that unitarity requires a delta function in the forward direction. And I'll explain to you why. So in the non-abelian case, this problem was studied by Bach, Jacques, and So-Young P. And I'll just tell you the result of their work. That considering the scattering of two particles in representation R1 and R2, the exchange channel is in the representation R. Let's say R1, R2 goes to R. Then if you solve the Schrödinger equation for the Aharonov-Bohm effect now for this problem, then it effectively behaves as if you have a U1 charge with a magnetic vortex with this type of flux, where C2R1, C2A is essentially the quadratic Casimirian representation R1, R2, and R. So R1 cross R2 goes into R, and this is precisely the magnetic flux, and this is a division by K, which is the level of the Chern-Simons theory. Okay. So the correct formula for the Aharonov-Bohm non-relativistic scattering is this one. and this is this factor of the forward scattering which I mentioned. And you'll notice one very interesting point here is that if you calculate the flux in the adjoint, the vortex charge in the adjoint and symmetric representation and the antisymmetric representation, it goes as 1 upon k. So for k large, this goes to 0. This is why you don't see the delta function in the T and U channels, okay? But for the S channel, the vortex charge is really finite and is simply given by lambda, okay? And therefore, in the S channel, you will see the delta function in the large n limit. At finite n, the delta function is there for all 3 channels. Okay, so now, what is the physical reason why you see this delta function, and how do you compute the coefficient of that delta function? The answer is actually very easy. That the point is that if you have a vortex, let's say a point vortex, and you do the Feynman path integral, then there will be paths actually which just go through the vortex in some sense. So what you have to do is you have to regularize the vortex by some little cutoff, and then there will be paths that go above and below, and you can really calculate, or what is the amplitude associated or the phase associated with the path slightly above and slightly below, and it just goes as e to the I pi lambda, and this as e to the minus I pi lambda. If you add the two and divide by 2, which is the average, you get that famous cosine of pi lambda. Okay, so this this cosine over here of pi nu is nothing but that. This minus 1 is the one that I said that if you write the S matrix as 1 plus IT, then you have to subtract that 1 from here. Otherwise, this is just the one piece, the identity piece of the S matrix. Okay, so now we understand after a lot of searching that if you do scattering in Chern-Simons theories which have anions in which the charged particles are automatically having fluxes with them, then you have to face the Aharonov-Bohm scattering. That is the main conclusion over here. Okay. So now there is I've spelled out a calculation over here of checking of unitarity, but in fact the delta function actually is needed for unitarity. I don't want to get into this. This is an elementary quantum mechanics problem. Okay, so the main conclusion is what I said, that scattering in Chern-Simons theory is very tricky, but once you realize that anions require a delta function in the forward scattering direction, I think you have made some progress, and that's the thing that we did. Okay, now point number 2. Since so this is the forward scattering delta function, but now crossing symmetry is not valid. So what do you do? So the reason why crossing symmetry actually is not valid is because the function is not analytic, okay, because of the delta function. And you have to rethink about how do you formulate scattering theory when the gauge field is very long ranged, or basically when you cannot switch off the gauge field, because your colored particle is always carry a gauge field vortex with it. So what do you do? How do you define the S matrix? So this is one definition which I'm going to give you. So the idea is the following. Let's go Euclidean, okay? Let's work in Euclidean theory, and let's think in terms of the volume being S3. I mean, take R3 and just compactify at one point for mathematical convenience, and then choose a large S2 sphere on it, actually, okay, inside it. So this is the S2 I'm talking about, and you can think of particles emanating from here, here, ending here, emanating from here, ending here, etc., etc. So this, without the red lines, was the process we were first considering, where you send in colored particles, they interact, and they scatter out. But now let's do the following. let us close these lines by Wilson lines, okay, so that these computations are completely gauge invariant. There are two ways of doing it. I mean, so let's define this as the problem with the punctured points x1, x2, x3, x4, and these are the Wilson lines in both these diagrams. Now let us consider T-channel scattering. If you look at particles coming from here, from here, from here, this will basically mean that a colored object starts over here and ends up over here, starts from here and ends up over here, or starts from here, coils around in a very complicated way with all these paths over here and arrives here. So the scattering, it's a very complicated type of picture, but ultimately what I want to say is that this is the type of topology of paths you will have in the T channel, and this is the one in the S channel actually. So now let's try to understand what's going on. Let me just point out something to you that in Chern-Simons theories at very large n, or in Chern-Simons theories, as you know, the famous result of Jones is basically about the question of how paths sort of cross each other, okay. So if you have a path over here like this, how does it cross? So there are three objects. This is the path on top, the path on the bottom, and there is a path that actually breaks up. So these three formulas are related by the famous Jones-Skine relations, which were derived by Witten using Chern-Simons theory. And however, what is very interesting is in the case of the large n limit, the Skine relation actually simplifies very beautifully. And what happens is that when particle paths cross each other, they just differ by a phase. The other term is not there at large n. So I use this qualitative point over here that if I look at the scattering of particles, undergoing very, very complicated intertwinings, I can remove all of them from bottom and below and bring all paths into this type of topology in the T channel and all paths in the S channel in this type of topology for the closed loop. So what I'm trying to say is that if you give a gauge invariant definition to the 4-point object which you want to compute from where you want to extract the S matrix, then you're forced into two types of paths which are topologically different from each other. So here you have one circle and here you have two circles, okay. Now I hope this point is clear, but this is a very important point because immediately you will realize that this being a Wilson expectation value of a Wilson loop, and this is a Wilson loop. So you have the square of Wilson loops whose average you have to calculate, and this is just one Wilson loop in the pure Chern-Simons theory. And as I mentioned to you before, the ratio of W squared to W, the averages, is precisely given by this sine pi lambda upon lambda, okay. And if you put everything together over here, just I told you the answer over here. I need to put in this factor. So if I start with the trial S-channel T matrix, which I get from crossing symmetry, naive crossing symmetry from the T channel, then I need to renormalize this answer by the expectation value of the Wilson loop, which is psi pi lambda upon pi lambda, as I explained just now. And this effect plus this delta function are really the new features of the scattering matrix when you scatter matter, colored matter in Chern-Simons theory. So this is the new thing, that you need a delta function and crossing symmetry fails, or you have new crossing symmetry relations for your theory. So So using this type of understanding, we calculated the S matrix for bosons. We calculated the S matrix for fermions. This is the explicit results for the bosonic theory. All these technical details have to do with the fact that we have to be near the Wilson-Fisher fixed point in this interacting theory, and you compute all this, and these are the final answers. You can prove the unitarity. This is the calculation, and we come to the fermionic theory. So the fermionic theory is this one. So you compute the S matrix there also now, and you find that once again you have to really, the same steps are involved, and once again you find that the fermionic S matrix in the T channel is given by this, and the S channel is given by these augmented formulae, and the T channel and the U channel S matrices actually do satisfy unitarity, and also the Fermion-Boson duality. And this is the main point, that we have calculated the S matrix for critical bosons and fermions. This can be done exactly. We learn a lot about this scattering theory because it's totally different from what you're used to. It has a forward scattering delta function because of anions, and it has a renormalization of the crossing symmetry from T to S channels, which I could explain by a gauge invariant definition that is to be used to extract the S matrix. So you learn a lot about S matrix in Chern-Simons. Where is all this useful? Firstly, one of the immediate applications of all this is to ABJ theory. ABJ theory consists of two Chern-Simons theories with opposite levels, and it has matter not in the fundamental representation, but in the bifundamentals actually. And ABJM is, of course, the matter is in the adjoint representation. Now, the point is that people have calculated perturbatively these S matrices, and they are not unitary. And clearly, one guess is that they are not unitary because they don't see the delta function. The delta function is very tricky to see in perturbation theory because you are using the light cone gauge, and the light cone gauge is a very singular object. You have to be very careful. I mean, I didn't tell you all the difficulties that we had, but if you do it all right, most probably the ABJ scattering theory will also be turning out okay. That is one project which one is looking at. And the other thing is that it will be very nice to understand the subtleties of the scattering theory at finite n and k, okay. And the last point I want to make, which is a problem which I have been sort of toying about, and which my belief in the importance of doing this was strengthened by Tony Leggett's talk, is that it will be very important to understand Majorana fermions. You couple to gauge fields in the orthogonal group, let's say ON plus 1. N plus 1 is, n is even, so n plus 1 is odd. So you have odd number of Majorana fermions coupled to Chern-Simons theory. What do you get? I don't know. I mean, this is a subtle problem. And I think it's related to the type of stuff which Tony Leggett was talking about. So it will be very interesting to look at these results. So thank you.
Any questions?
Can you make any estimate if you use say 1 over any expansion, then correction to that kind of analysis or so?
I think that would be a technical problem which I think will be quite hard to do. But what I was having in mind was, can we make some general comments actually about the S matrix for finite n and finite k? So I believe that the delta function will be there for finite n. I think we see very physically a very simple result. But how to renormalize the answer from the T channel to the S channel, this is not clear at all, actually. Also, I'll tell you why it is not clear, because I used the simplification of the skein relations in order to argue that the paths fall into just two topologies, two circles or one circle. If n is finite, then the skein relation of knot theory is very complicated, and I don't know what to do, actually. Okay.
What is the gravity dual of
yes.
this theory, and what is the duality of this duality symmetry you have?
So the
between
duality
bosons and
symmetry
fermi?
I'm talking about at the moment is in the quantum field theory only. It is Chern-Simons theory coupled to fermions. Yes. But now, of course, as you know, that this theory is dual to Vasiliev theory when the matter is in the fundamental representation. So yes, so many of these things actually carry over into Vasiliev theory. Now, we have not actually seen how to do the calculation of what the delta function means, etc., in the dual. That's a very interesting question. I don't know the answer to your question. But the 3-point functions have been computed. We can understand partition function, etc. But I think these subtleties of the scattering matrix, what they mean in the dual theory, I don't know. But it's a very good question. Yes.
Our last question, if anyone has. Okay, let's thank Spenta again. I think we get a coffee break.